In the world of artificial intelligence, handling structured knowledge like tables, databases, and knowledge graphs is crucial for tasks such as answering everyday questions or supporting complex applications. This research paper introduces a new framework called Pandora, designed to unify the way large language models reason across these diverse sources. Let's break it down step by step. Structured knowledge reasoning, or SKR, involves using organized data to answer natural language questions. For example, imagine asking a system to find all books written by J.K. Rowling that were published after 2005. This could draw from a database, a table, or a knowledge graph. Traditionally, methods for SKR have been task-specific, meaning they're built for one type of data, like SQL for databases or SPARQL for knowledge graphs. This approach limits the ability to transfer knowledge between tasks, making it hard for systems to learn from one type of data and apply it to another. The authors of this paper argue that a better system should handle all these sources in a unified way. They point out that real-world applications, such as medical decision support or legal analysis, often require integrating multiple types of structured knowledge. For instance, a doctor's system might need to query patient databases and drug knowledge graphs simultaneously. Existing unified frameworks like StructGPT, ReDI, and TrustUQA try to address this by using task-specific strategies or custom representations, but they fall short, especially in covering database reasoning effectively. Enter Pandora, a code-driven agent built around large language models. The key innovation here is using Python's Pandas library to create a unified representation of all structured knowledge. Pandas is a popular tool for data manipulation, and it's familiar to many AI models because they've been trained on vast amounts of code. By converting tables, databases, and knowledge graphs into Pandas-based structures, referred to as Pandora's box, the framework aligns the data with what large language models already understand. How does it work? Pandora has three main components: a well-aligned large language model, a reasoning memory, and a Python interpreter. When you input a natural language question, the large language model first generates textual reasoning steps. These are like step-by-step explanations of how to approach the problem. Then, it produces executable Python code that uses the Pandas library to query and process the data. To make this even more effective, Pandora draws from a memory of training examples. This memory includes demonstrations from various SKR tasks, allowing the system to transfer knowledge across them. For example, if the model has learned how to handle a table query, it can apply similar logic to a database or knowledge graph query, thanks to the unified Pandas representation. The paper illustrates this with a figure showing how a simple question can be translated into SQL, SPARQL, and Pandas code. Even though the syntax differs, the underlying logic is the same, and by standardizing it through code, the large language model can reason more consistently. Why is this approach better? First, it facilitates knowledge transfer. Instead of treating each task in isolation, Pandora lets the model learn from a broader range of examples, improving performance on new tasks. Second, it leverages the strengths of large language models, which are pre-trained on programming languages and excel at generating and understanding code. This reduces the gap between the input data and the model's inherent capabilities. The researchers conducted extensive experiments on 4 benchmarks covering 3 main SKR tasks: table question answering, text to SQL, and knowledge graph question answering. The results show that Pandora outperforms existing unified frameworks and even holds its own against methods designed specifically for individual tasks. This demonstrates that a unified approach doesn't have to sacrifice accuracy. In fact, it can enhance it through better knowledge sharing. Delving deeper into the methodology, the paper explains how they transform different knowledge sources. For tables, it's straightforward: convert them directly into Pandas data frames. For databases, they map the schema and data into a similar dataframe structure. Knowledge graphs, which are more complex with their nodes and edges, are also adapted into a tabular format that Pandas can handle. This transformation ensures that the large language model can interact with all sources using the same tools. One of the challenges addressed is ensuring the generated code is accurate and executable. The Python interpreter in Pandora runs the code and checks for errors, providing feedback if needed. This iterative process helps refine the reasoning steps, making the system more robust. The authors also discuss the broader implications. In applications like investment analysis or disease diagnosis, where decisions rely on multiple data types, a unified framework like Pandora could streamline processes and reduce errors. By relying on code as a common language, it opens up possibilities for more flexible and scalable AI systems. To evaluate Pandora's effectiveness, the experiments included metrics like accuracy and execution success rates. For instance, on benchmarks involving tables, the system achieved higher precision by generating precise code snippets. In knowledge graph tasks, the ability to transfer learning from database examples led to improved question answering performance. Overall, this framework represents a shift toward more integrated and efficient reasoning with structured knowledge. It highlights how aligning data representations with the strengths of large language models can unlock new levels of capability, paving the way for advancements in AI-driven applications.